We can think about using projections in order to understand rotation matrices. If we think in terms of dot products, we will remember that if we have two vectors, one vector A and one vector B, then A dot B, right, the scalar product, is given by cosine theta if they're unit vectors. Generally, A dot B is given by the magnitude of A times the magnitude of B times the cosine between them. But as I said, if these things are unit vectors, then projection of A onto B is just given by the cosine relation in this particular case. So we can use these in order to specify projections of one frame onto another frame. Let's think about projecting now x1 onto x0. Well, we know that that projection is going to be, then for unit vectors, is going to be cos theta. If we project x1 onto y0 though, right, that's basically going to be the sine theta term. So we have two relations depending on which one we're projecting it onto. Here we're projecting it onto x0 and here we're projecting it onto y0. So this would give the projection for these, for basically for the x0 and the y0 unit vectors. We see that we end up with the mapping that x1 is given by the following transformation of a data point, which is given by basically a cos term multiplied by the x and then a sine term multiplied by the y. And if we carry on and look at them, what do we get for the projection onto the y-axis? We see, first of all, we get, well, y1 projected onto x0 gives us minus sign now because it's basically going the other way. And y1 projected onto y0 gives us cos theta. So we end up with the x-axis mapping as follows. So this would then be multiplied by a data point in order to get the y1 value. And if we concatenate those two together, then we end up with the rotation matrix we had before that gives us then the way to transform x data point, x0 and x0 and y0 data points back into the coordinate frame. We can use projections in order to analyze things in 3 dimensions as well. The x and the y projections are just exactly as we said before. If we rotate around z, then obviously nothing changes in z, right? We're not moving any of the values in z, so z projects completely onto it. Z1 projects completely onto z0. So we have a z1 dot z0 equals 0. So this would be the full projection matrix in order to do a rotation. So the first term would be x1 projecting onto x0, y1 projecting onto x0, z1 projecting onto x0, x1 projecting onto y0, y1 onto y0, z1 onto y0, and then x1 onto z0, y1 onto z0, z1 onto z0. Consequently, if we put in the upper 4 values that we had before, we end up with the cos minus sine cos terms. We notice also that z1 doesn't project at all onto x0, right? This is orthogonal with x0, so that this term is 0. Z1 is also orthogonal, right? There's no relation of anything here with anything down here, so this is also a 0. And z1 projects 100% onto z0, so that value is 1. So that's why we get these values here. So let's think about rotation matrices then. If we rotate around the z-axis, we end up with a transformation matrix which looks like this. Cos minus sine 0, sine cos 0, 0, 0, 1, so it has no effect on anything in z. But we can then basically do the same for any axes. So the corresponding rotation around x isn't going to change the values in x at all, but it will change the values in y and z, right? So if we rotate around x, then y and z will change as we rotate, And similarly, if we rotate around y, then values in y aren't going to change at all, so there'll be a 1 in there. But the z and the x values are going to change. So we end up with a set of 3 formulas which basically relate to mapping round rotations around different axes. First one being z, second one being x, third one being y. Always in the positive direction. If you remember the right-hand rule, the thumb gives you the direction of the axis, and positive is the way the fingers curl round. So these are the 3 equations that you'll be given anyway. You wouldn't necessarily be expected to remember them. Quite often you'll see the rotation matrices written in this different form. So rather than writing cos theta, there's a tendency to write c theta, and sine theta goes to s theta, right? So it's just basically a shorthand. Cos theta equals c theta, sine theta equals s theta. So these 3 formulas, either in this form, fully expanded, or in the shorthand version, are very useful because they come up a lot in rotating around things, particularly when we're doing Denevit-Hartenberg rotations. We'll be rotating stuff around z, and we'll be rotating stuff around x a lot. So you have to use those formulas a lot. It's very easy to build these kind of things up in Matlab. Probably some of you have already done it. They are also available in the robotics toolbox, but basically you can easily set up a function. You want to calculate your sine component and your cosine component. In this case, I'm actually giving it values in degrees, so I'm using the cos d function rather than the cos. Cos will take a radian argument. So you just build up the elements in the rotation matrix by concatenating the elements. So 1, 0, 0, right? And then we put in another row, 0 cos theta minus sine theta, put in another row, 0 sine theta, cos theta, and so on. Same principle for building your own first principles rotation matrix around the y-axis. You just use the y formula, or around the z-axis and you use the z formula. So imagine now we want to compute a vector, in fact the position vector, by rotating one already by 30 degrees. So all we have to do is we just define the point that we want, we build our rotation matrix, and we multiply our point by the rotation matrix, and then we end up with a new value, right? So it's as easy as that. So now imagine 2 rotations, one about the z-axis by 30 degrees and one about the x-axis by 30 degrees. Well, we're going to see that actually does make a big difference what order you do them in. So that's something you have to bear in mind with rotations in general. In fact, rotations and translations, we can't just swap them round. That means they're non-commutative. Commutative. I always get that word wrong. Think about commutative being like in terms of moving around on, like commuting, right? Can you move things around and does it still work? If you can't, they're non-commutative, and you can't just change arbitrarily angle and translation orders around when we're doing these things, because you'll get a different value coming out. So here we're going to do a rotation matrix around the z axis by 30 degrees. We're going to you build it up using the function we gave you. I just showed you before. Another rotation round the x-axis by 30. So one way round is going to be you first do 30 degrees round the x, then you do 30 degrees round the z. The other way round is that you first do the z and then you do the x. If you look at the 2 results, you'll actually see that they are actually different. So that's just a very basic demonstration that it does matter, and matrix multiplication of rotation matrices is non-commutative in general.